I'm Ethan Kwan, and today I'm going to be showing you what the universe will look like in not just a few billion years, but a trillion years, a quadrillion years, a quintillion years, like 10 to the 65 years, or whatever. So we're gonna go to the end of the universe. Okay, so the universe is divided into 5 main periods. I forgot to add that. The primordial era from t equals 0 to 4 billion. The stelliferous era, so t equals 400 billion to now to 10 to the 13th. We live in the stelliferous era. The degenerate era, t equals 10 to the 13th to 10 to the 40th. The black hole era, from t equals 10 to the 40th to 10 to the 92nd, and the dark era, t equals 10 to the 92nd to infinity. So the first two are straightforward. Primordial era, the time between the Big Bang and the first star that forms. Stelliferous era is now until the last star. So basically from the beginning, the first stars to the last stars. So here's the Milky Way, and this is what it looks like now, with a lot of blue stars illuminating it, right? Now, in a few billion years, all those blue stars would have died away, and it would probably look something like this. It would be yellower, and a little bit red. Now, in a few more billion years, it might look like this. Really red. And in a few billion more years, it might look like this, kind of dull, and it's mostly made up of white dwarfs, neutron stars, and black holes. Now, so white dwarfs, neutron stars, black holes, and actually brown dwarfs as well, those failed stars. Most of these objects are held together by either electron or neutron degeneracy. I've practiced this word for a long time. Electron and neutron degeneracy pressure. Electron and neutron degeneracy. I can't say it. Degeneracy pressure. I said pressure wrong. Okay, whatever. Anyway, so let's say there are 2 atoms, and the outer shells are electrons, so they're technically negative. So the outer shells so if 2 atoms come into too close contact, they will want to repel each other. The same with neutrons. It's interesting because neutrons don't really have a repellent force, but if they get super close, they actually do. Interesting. So most of these objects, not including black holes and of course brown dwarfs, not including them, are made from degeneracy pressure, so that's why we call it the degenerate era. Oh yeah. Galaxy spin! Woohoo! Yeah! Wow, I'm getting dizzy. Never mind. Okay, this is not cool. Stop, please. Yeah, thank you. Okay. So, this era will be pretty dark. So, it would be, not that bright. So, in a few billion years into the degenerate era, most of everything will be about room temperature. And as we go farther into the degenerate era, the colder they'll be. But they will have a few big explosions that make them really hot. For example, neutron stars colliding. See? It's really bright. And also brown dwarfs colliding, because brown dwarfs, when they collide, they could actually produce a fairly normal, if low mass star. So like a red dwarf. That could burn for trillions of years. So that's actually a better source of energy than explosions. Pretty cool. Okay, so, some kind of weird, of course the degenerate era has to end eventually, and what ends it? Interestingly enough, decaying protons. So, an event like this, protons do decay at really long periods of time. So, for example, 10 to the 4, weirdly, protons do decay at with really long periods of time. So, here's the time period. 10 to the, wait for it, 10 to the 34. That is 10 followed by 34 zeros. Wow, that number. Ta-da! So, this number is appearing on your screen right now. It has 34 zeros. This is a big number. Yeah. So, not as big as most numbers that you're going to encounter on this episode, but this video, not episode, sorry. I think I've watched too many, podcasts. I think I've listened to too many podcasts. Anyway. So, 10 to the 34 years. It takes 10 to the 34 years for a proton to decay. But the universe can wait. As protons decay one by one, everything that is made of matter will decay. So, for example, a star, or a neutron star, or a white dwarf. Those kind of things. Watch. They decay really slowly, but time can wait. I wish it would stop already. Hello? Can you stop? Well, it's not listening to me. The computer isn't listening to me. Stop it! Anyway, okay, whatever. It's not gonna stop because it's just doing its own thing, which is really being annoying. Okay, that was the last explosion. Now, can the last explosion just stop? I'm almost there. Okay. There is an upside, kinda. So as these decay, it would actually release a little bit of energy, about 400 watts. Mind you, a microwave oven in the kitchen produces more power, but since it's really dark, it will look like a really bright star. So, in 10 to the 40 years, all matter would have been gone. So, for example, so anything made of matter, white dwarfs, neutron stars, and brown dwarfs would have actually decayed into nothing. The brown dwarfs going first, and then the white dwarfs, because they have less gravity, never mind. And then go the neutron stars. Now, what's left? Black holes. Interestingly enough, black holes won't decay because, well, nothing can escape. Unless it's going faster than the speed of light, which is impossible. Almost. Yeah, there's a phenomena that makes things can go at faster than the speed of light, but interesting, okay. Anyway, so the only things left would be actually black holes. So, now we go from the degenerate era to the black hole era. Oh no, I made the galaxy. I'm dizzy now. Stop it. Okay, it stopped. Anyway, so black holes don't really do anything. they just sit there unless they consume a large amount of matter, like if a wandering star passes too close, which is like really weird, and I don't know why they would do that. Then it would produce an accretion disk. Yeah. Why is it still in the black hole? That's strange. Okay, there it goes. Okay. So it doesn't really do anything. Like, of course, black holes may collide with other black holes, but that is also not really gonna help, like, the darkness. So it's kind of gonna be boring here, but interestingly enough, black holes do have a way that they can emit energy. They evaporate like this, really slowly, but interestingly enough, they can. It's called Hawking radiation. So Hawking radiation is just like really slow, like, and it just evaporates the outermost layer by a little bit. But in the black hole era, it'll be only black holes, and well, they will evaporate. So let's say we have a black hole that is 3 solar masses heavy. So this is the minimum size for one created in a supernova. So this will take about, for it to evaporate, it will take about, the number's coming up, don't worry. Come on, you're almost there, the number's almost there, come on, get bigger already, number, hello, number, can you hurry it up already? I have a really busy schedule, so just hurry, please. This is annoying. Boo the number, please, everybody. Just type boo in the comments, or boo this number. Just write boo this number. Okay, I think it's almost done. OMG, the tiny black hole over there. It'll take 10 to the 68th power years to evaporate. That is a long time. But the universe can wait, of course. Now, let's say there is a black hole at the center of a galaxy. How long will it take for those black holes to evaporate? Well, I'll give you the answer. This number, or 10 to the 92. 10 to the 92nd power. This is a huge number. There isn't really a concept for it. This number has, if you put this many, this number is bigger than the number of atoms in the universe right now. That is really big. After this, there's really nothing that is left. Because all the black holes evaporate after 10 to the 92, 93 years, nothing will exist. We have entered the dark era. Now, oh, no, not the galaxy. No. Okay, I'm getting dizzy. Stop. Okay, I said stop. It stopped. Okay, so the dark era is dark. Really dark. I mean, like, seriously, this is not fun. Well, it is, but, like, this is not really fun to think about. Like, in 10 to the 92 years, nothing will exist. Not stars. Oh, wow. Stars are just dropping away. Sad. Beep, beep. Wait, what? I think it takes, like, 1 second. Every second, it drops the number by 1 star. Weird. There won't be any planets. No planets. This is really strange. no planets or anything. Now there's another theory. It's called the true vacuum theory. So let's imagine this with a staircase. You've been standing on what you think is the bottom stair, but then you find out that you're one stair up from the bottom stair. This is where the universe is. Well, in this theory. It is one step up. So we think of the vacuum of space as nothing. There's nothing in it. But there might be an even lower energy state that we don't know about yet. Now, it might be that our universe is just balanced on this step. But if something knocks it down, down it goes. So, what happens when this little section drops down to the next lower energy state? Well, it will bump the ones next to it. And those will bump the ones next to it. And so on. It'll make a chain reaction that goes out from the blast that kind of like ruins your day. What is left is something new, something different. This is just a theory, but maybe it's like another Big Bang. So maybe our galaxy was formed from a really old other galaxy that did this. Maybe it'll happen again and again and again. This is actually fun to think about. It's just a repeating cycle that goes through many, many universes without ending. This is pretty cool. Okay, so that's all the topics I want to talk about today. So, thanks for watching. If you like this video, go watch my other videos on my YouTube channel. Also, don't forget to subscribe and hit that bell icon so you won't miss out on any videos. Bye! I have to breathe, sorry. Whew. Stop the video. 3, 2, 1, stop!